So let's look at an RLC series circuit. Now, the order of this RLC, it could be LRC, it could be CRL, any of them. We just mean R is our resistor, L is an inductor, C is a capacitor. So we're essentially saying we have an alternating source attached to a resistor, an inductor, and a capacitor. All in series is what we're going to look at. The order in which these three are connected is not, it doesn't matter. What matters is that they are in series. Now, that's not the only way they can be connected, but we are specifically going to look at the equations and the phasor diagram to represent them connected in series. So our source voltage is alternating with time. And if you recall, with the resistor, when we talked about just the resistor, the voltage drop across the resistor and the current flowing through the resistor are in phase. We just talked capacitor in the last video. The voltage drop across the inductor and the current flowing through the inductor are out of phase. Specifically, the voltage leads the current by 90 degrees or pi-half radians. With the capacitor, the voltage and the current were out of phase for that as well. And specifically, the current was leading the voltage by 90 degrees. Because of these phase differences, we have to use the phasor diagram to relate these three together. Now, the current, we know there's going to be current flowing. The amount of current flowing at any moment in time is going to depend on the overall ohms in the circuit, so that depends upon the angular frequency of this source, as well as the element values like L and C and R. So we're going to draw a phasor diagram to represent this and relate all of these three elements together to that source voltage. So our phasor diagram, we just draw a coordinate system, and we can draw the vectors that represent these phasors at any one moment in time. If you recall, the length of the phasor or vector we draw is representative of the maximum or peak value. At any one moment in time, we can add the phasors vectorially. Now, to do this in the simplest way that I can think of, I first want to come back to my circuit for a second. My series circuit, if we think about back to, say, resistors in series. Now, I know these are not all resistors, but in series, they all have to have the same current. And that's because there were no additional paths. There's no branches where some current can go along one branch and the rest can go through a second branch. Knowing this, I am going to draw my current phasor first, because I know these three, the current everywhere in this circuit has to have the same value at any one moment in time. To make my vector addition easy, I'm going to draw my current phasor on the x-axis. All that means is I am looking at a single moment in time where the current is a maximum positive value. So at this exact moment in time, the current in this circuit is maximum. what I need to do now is draw my voltage phasors. The resistor phasor is probably the easiest to draw because we know the voltage drop across the inductor is in sorry, I don't know why I put an L on that. Okay, my current phasor, RLC, meaning the current through this circuit that has all three, resistor, inductor, and capacitor. This phasor I just drew now represents the maximum voltage drop across the resistor specifically. I know current and voltage are in phase when we have a resistor. So IRLC, this capital I, represents the maximum amount of current that will flow in the circuit. Now the inductor and capacitor. Inductor, the voltage for the inductor leads the current by 90 degrees. So I need to go ahead of my current phasor by 90 degrees and draw the voltage across the inductor's phasor. So what this means, since I've chosen a moment in time where the current is a maximum value, at this exact moment in time, the voltage drop across the inductor will be 0, which is fine. Now I need to draw also the phasor representing my capacitor. With the capacitor, the current leads the voltage by 90. That means I need to go back 90 degrees and draw the phasor representing the voltage drop across the capacitor. Now, whether VL or VC is bigger depends upon the circuit. That depends upon the rate at which the source voltage is oscillating at. Let me draw one of them a little bit bigger so that it's obvious. VC could totally be bigger. We'll look at that in a second. So at this moment in time, if we add these phasors, which are vectors at this moment, the VL, the VC, and the VR, at this moment in time, the resulting vector will represent the maximum source vector. Okay, so VL and VC, if we add head to tail, we end up just coming back VC like this, and then adding VR coming out here. Our resulting vector is right here. So this is just tip to tail vector addition. The length of this represents the maximum source voltage. If we think of this as a nice little triangle, this horizontal side is VR. This vertical side is the magnitude of VL minus VC. VL and VC are always exactly opposite each other. So, Pythagorean theorem, if this is a right angle, I can say that the hypotenuse squared must equal one side squared plus the other side squared. But in series, they all have the same current. So what I want to do is I want to substitute in place of the resistor, I times R, in place of the inductor, I times X sub L, in place of the voltage for the capacitor, I times X sub C. So those are all the relationships we came up with, I in each of those is IRLC, meaning the current in this series RLC circuit. So I could write this way. The current is the same for all of them. So I could factor that out. That would leave me with an R squared plus this quantity of XL minus XC squared. If I take the square root of both sides, I get this maximum source voltage is equal to IRLC times the square root of R squared plus this quantity of XL minus XC squared. Units though, volts is equal to amps times ohms. This quantity right here must have units of ohms. We call this impedance. Our author uses a capital Z to represent it. This is the overall ohms in the circuit, the overall resistance to the flow of current. The total amount of current that flows in the circuit, the peak value, would be the peak source voltage divided by this impedance. So anytime we have a circuit with all three elements, we will need to relate the source voltage to the current through this impedance. R is the value of the resistor, XL is the omega L, XC is the 1 over omega C. And so we can relate these three elements together by way of this impedance. So this is our ohms. It's not a true resistor, but it does directly tell us how each element works together and affects the amount of current flow. Now coming back to our diagram, notice there is an angle phi between that source voltage vector and the current phasor. If we were to write the equation that describes the current as a function of time, it would be a cosine function with a phase shift. We don't put the knot on this, I forgot. So here, this phase shift phi is the angle behind or between the source voltage and the current phasor. And actually, let's see, current is behind, so I think that would be a minus. That phase angle is actually relatively easy to calculate. In that triangle itself, we can say the tangent of that phase angle would be the opposite side, the VL minus VC, over the adjacent side. Now we do have to have them all in terms of voltages to make this relationship. So we're using that triangle that represents the voltage, the sum of those voltage phasors. I know the inductor can be written as I times XL. The capacitor can be written as I times XC. The resistor can be written as I times R. So the currents, again, since we're still talking series, the currents will cancel. And we can say that the tangent of that phase angle is XL minus XC over R. This equation's on the test notes for us. You don't need to derive it again. In this picture, in this diagram, I did choose to make VL, the maximum voltage drop across the inductor, larger than that for the capacitor. And that is why we got a voltage leading the current by phi. If I had chosen to draw the phasor for the capacitor's voltage larger than the inductors, when we added them together, we would have ended up with a result over here. That would be our voltage. And then the phase angle would have been behind. So XC bigger than XL, we find that the current leads the voltage by phi. If XL is bigger than XC, then the voltage leads the current by phi. There's a really silly acronym. It's even in the book. I did not make it up. Eli, the ice man. L, inductor. In Eli, the EMF is before the current. So if XL, LLL, is bigger than XC, then the voltage leads the current. Eli. C for capacitor. In ice, I is before C, which EMF, E, at the end. If the capacitance, or X sub C specifically, is bigger than XL, I comes first in the word, current will lead the voltage by 90 degrees. So, silly acronym to help remember the difference. Now, by the way, this equation in and of itself will give you which one? The phi. If phi ends up being positive, if phi is positive, then XL is bigger than XC. If phi gives you a negative answer, then you know XC is bigger than XL. Okay, so main equations so far. Z, the impedance. The overall current that flows in the circuit is directly related to the source voltage and inversely related to that impedance. The overall angle between the voltage and current can be determined with this tangent inverse equation. Let's talk just a little bit more about power. Power of the source. Now, this is actually incorrect in the test notes. That's my fault. I typed it in wrong. The power of the source is equal to IRMS times ERMS times the cosine of phi. Now, the cosine of phi, we're talking this same angle phi that was in our phasor diagram. Cosine of phi would be the adjacent side was the resistor's voltage over the hypotenuse, which would be the source voltage. Well, we know the resistor's voltage is I times R. The source voltage we can write as I times Z. But again, since we're talking about a series circuit, these have to have the same current. So we find that the cosine of phi Oh, hush. Sorry. Siri thought I was talking to her. So cosine of phi ends up equaling R over Z. We call cosine of phi the power factor. If R is equal to Z, then cosine of phi has to equal 1. Well, if we relate that back to the power, if cosine of phi is 1, then the power put into the circuit by the source would simply be IRMS, ERMS. But R and Z do not need to be equal to each other. Oftentimes, R will be less than Z. And by the way, R cannot be bigger than Z. If you come back up here to the impedance equation, there's no way that R can be bigger than Z. But if R is less than Z, then our power factor is less than 1. So coming over to this power, if the cosine of phi is less than 1, then the power put into the circuit source is smaller than IRMS, EMF RMS. Ultimately, if that phase angle, that cosine phi, if that power factor was, say, 0.8, I'm totally making up 0.8, then we would say the power put in by the source is 0.8 of this IRMS, ERMS. So 80% of the total possible power is going into powering the circuit to create the heat, the light, whatever it is that the circuit is meant to do. It turns out when we have a power factor that is not 1, some of the energy is just going into oscillating the energy between the inductor and capacitor. Ultimately, if we want to talk about the energy actually going into the heat, the light, whatever the resistor is supposed to do, if we talk about the power dissipated by the resistor, we can say that that is IRMS times delta V for the resistor RMS. But the resistor we know is I times R, so we could say this is I squared R. But it's specifically IRMS. The RMS values. ERMS is the max over the square root of 2. IRMS is the max over the square root of 2. So this power dissipated by the resistor, if we plug in, this would be the IRLC that we talked about just above there. If we plug that in for IRMS, we end up being able to say that the power dissipated by the resistor is 1/2 of that max current squared times the resistor value specifically. If we come back to the source and want to plug in these RMS versus max values, we end up with 1/2 IRLC times the E max times the cosine of phi. When you look at the test notes for the equations for power, they're on the following page after this current and voltage. So the equations span 2 pages. Now I know there's been a lot of equations, so we'll do a couple examples. You're going to find that we mainly use the relationships that connect the maximum values together. So you'll find that hopefully it's not as intimidating as it originally appears to be.